Traditional orthotics rely on a static mold, captured while a foot is at rest. But the moment human mass collides with the ground, the foot undergoes massive physical deformation. Rigid plastic cannot adapt to these changing kinematic loads. Take a condition like flexible flat foot. While seated, the patient's medial arch appears normal. However, the exact moment weight is applied during a step, that entire structural bridge collapses inward. Notice this vector breakdown. Plantar forces change by the millisecond. The medial arch plunges under weight-bearing stress, and kinetic loads shift with fatigue, terrain, and gait phase. To address this, an active orthosis continuously tracks and mechanically responds to shifting loads in real time. This responsiveness depends on material stratification, stacking highly specialized physical layers into one precise unit. Stratification decouples conflicting mechanical requirements. The porous material needed to maintain skin comfort is poorly suited for measuring kinetic data, and the electronics needed to gather data cannot physically prop up a collapsing arch. By separating these functions, we replace the rigid cast with a real-time, responsive, multi-layered architecture capable of directly managing dynamic foot pathologies. We begin at the top with Layer 1, the dermis interface. This is the primary contact point between the orthosis and the patient's skin. Its role is strictly environmental. It manages moisture buildup, dissipates thermal energy, and minimizes friction against the plantar surface to prevent skin breakdown. This soft interface acts as a physical buffer, translating the rigid internal mechanical components beneath it into a wearable surface, ensuring the patient can tolerate the device for 12 to 14 hours a day. Directly beneath that barrier sits Layer 2, the pressure sensing layer. Here, physical comfort gives way to diagnostic hardware. This layer consists of an embedded piezo-resistive sensor matrix. These sensors are distributed across key load-bearing zones: the heel, medial arch, and metatarsals. As this heat map demonstrates, the matrix captures high-resolution plantar pressure data. It maps kinetic loads continuously, tracking the distribution of weight from the initial heel strike to the final toe-off. Embedding this matrix shifts treatment from episodic clinical guesswork to continuous real-world kinematic observation. Moving deeper, we reach Layer 3, the adaptive support layer. This acts as the active force redistribution engine, utilizing a modular structure of internal pressure cells. Operating on the mechanism of variable stiffness, this layer reacts directly to the live sensor data above it, physically altering its localized rigidity to tighten or soften specific regions of the footbed. Clinically, this allows for the dynamic offloading of painful epicenters. In cases of plantar fasciitis, the layer redistributes the mechanical force away from the inflamed tissue and transfers it to healthier load-bearing zones. This active force management sits directly above Layer 4, the arch support layer, which features an anatomically contoured midfoot zone. Notice the vector lines isolating the medial contour, providing the exact counterforce to prevent excessive arch collapse in flexible flat foot. Correcting this angle prevents the ankle from rolling inward, which subsequently realigns the entire kinetic chain, including ankle and knee joints. While Layer 4 provides the structural anatomical boundaries for the foot, Layer 3 actively manages the live forces operating within those boundaries. Stability requires a firm anchor. Layer 5 is the heel stabilization layer, characterized by a deep, rigid rear foot cradle. Calcaneal movement control is essential to prevent rear foot eversion. This rigid cup locks the heel bones squarely in place, halting the side-to-side rolling that destabilizes a patient's stride. By stabilizing the heel, the device anchors the initial phase of the gait cycle. This yields superior step control from impact and reduces systemic instability across the leg. Directly beneath that anchor is Layer 6, the cushioning and shock absorption layer, with dense, targeted zones isolated under the heel and the forefoot. This layer relies on the physics of impact dampening. It absorbs and dissipates kinetic shock waves generated when the foot forcefully strikes a hard surface. Dissipating that shock yields specific clinical outcomes. It decreases muscular fatigue in the calves and mitigates the harsh microtraumas that travel up the lower extremities. Rigid heel anchoring provides trajectory control, while targeted shock absorption neutralizes impact force. Both are prerequisites for preventing kinetic chain failure during locomotion. All previous components rest inside layer 7, the structural base layer. This is the mechanical chassis of the entire orthosis. Absolute baseline rigidity is required at this level to ensure the device maintains long-term shape retention, resisting deformation even after millions of load-bearing steps. The exterior bottom surface of that chassis is layer 8, the shoe interface layer, manufactured with a high-friction, anti-slip texture. This creates mechanical coupling. The orthosis must remain immobilized within the host footwear to ensure anatomical alignment is not compromised during movement. Finally, embedded within the chassis is layer 9, the compact electronics and interface module. This schematic maps the electrical power and data routing to the upper sensing layers. This is a practical communication hub. It houses the battery and microcontroller, powering the sensors and transmitting clinical data out to an external application. Without the stability of the structural chassis and the physical coupling to the shoe, the precision of the data and adaptive components would be neutralized. When these 9 distinct layers compress down, they form a single unified medical device. Orthopedic innovation arises from the precise orchestration of sensing, stabilization, and mechanical adaptation working simultaneously. Look at the closed-loop workflow. The system executes continuous data collection, calculates the pathological load, and immediately triggers a localized actuation response to physically support the foot. This architecture empowers practitioners to monitor longitudinal patient progress, capturing exact kinematic data as the patient navigates their daily routine far beyond the clinic. Because it is dynamic, the device adapts to the patient's recovery trajectory. As a pathology like plantar fasciitis improves, the system actively alters its support profile, tapering intervention as the tissue heals. By stratifying these specialized functions, this active architecture resolves complex foot pathologies dynamically. It bridges the gap between clinical diagnostics and continuous daily biomechanical support.